So today I'll do more questions on this friction. I think I've downloaded the file, right? Let me go. Yeah. So now we will go to slightly more tougher questions. Look at this. Let me copy this. So questions of these type where they are not giving the value of the force and they are asking you what will be the force where both blocks move together, or what will be the force where they slip, things like this. These are a bit complex questions. So let's try to read this question. What he's saying is find the maximum possible force. So this is the force which he's applying, and you have to find the maximum value of that to move both the blocks together. So you have to find the maximum force up to which both blocks move together. If you apply very small force, probably they'll move together. But as you start increasing this force, there comes a stage where you are like pulling the 8 kg with huge force. You are pulling the 8 kg with huge force, and it might separately move, and the 5 kg may not move along with it. So the friction between them becomes kinetic. So indirectly he's asking the force where the friction between these two is tending to kinetic, or it reaches the maximum value of static friction. Now how do we solve these kind of problems? So what you do, we again start with the same assumption that let blocks move together. And in this also there are two cases he's asking. One case is bottom surface. Remember, the bottom surface is frictionless, means here there is no friction. That is one case. The other case is bottom surface has friction of coefficient 0.3. So let's do it step by step. So first I'll do case A, bottom surface is frictionless. Now what he is asking is you should find the maximum value of F up to which these two blocks move together. It's like, if you apply 0.5 Newton, they may move together. 1 Newton, they may move together. As you keep increasing this force, there comes a stage where 8 kg would accelerate too much and it would break the bonds with 5 kg and run away. It would break the bonds with 5 kg and run away. That force where it is breaking the bonds with 5 kg, that I have to find. So what I'll do, let's assume blocks move together. I don't know the value of F, but I'm assuming this. Blocks move together. In that case, I can draw the combined free body diagram. So there is a 13 kg block now. Okay, 8 plus 5 is 13. And you are applying some force, and bottom is frictionless anyway. So we are lucky there. So acceleration of this system is F by 13. We got the combined acceleration. What we are going to do with that? Well, with combined acceleration, I'll find friction between the blocks. And as long as this friction is static, they will move together. But static friction lies between 0 and mu s n. So I'll apply that condition and try to get the values of capital F for which the blocks move together. So it's like this now. I'll take the upper block, the 5 kg block I'm taking. We already got the acceleration F by 13. And there is static friction on 5 kg. Top one is 5 kg, bottom one is 8 kg, right? So I'll just write that way only. It's better. Top one is 5 kg and bottom one is 8 kg. So if both are moving together, you should ask the question, why is the upper block moving? It is because of this friction only, which is static, because I assumed they move together. And how to get this static friction? There is no formula. I have to apply Newton's law, so I'll apply it. So net force, which is F in this case, is mass, which is 5 into acceleration F by 13. Combined acceleration is F by 13, so I'm taking independent acceleration also as F by 13 because they're moving together. So I got the friction. If really the blocks are moving together, this friction should be static. But static friction lies between 0 and mu sn. And what is the mu s given between these 0.4? You see here it is given to be 0.4. And n at this junction will be equal to the weight of 5 kg, because this 5 kg is in equilibrium. So it will be 50. So I can say 0.4 into 50. This should satisfy. As long as this satisfies, the blocks move together. The friction is static, they move together. But we got this friction in terms of applied force. So 0 less than 5f by 13 less than 20, which implies 0 less than 5f less than 13 into 20 divided with 5, which means 0 less than f less than 52. So as long as f lies between 0 and 52, till that point the friction lies between 0 and mu sn, means it is static. Until that force, the blocks move together. So up to 52 Newton, so up to 52 Newton, blocks move together. The moment you increase the force to 52.5, the blocks separate. 8 kg moves separately. There will be kinetic friction. 5 kg will also move separately because of that kinetic friction. Okay, so this is the idea. So what we have done, he's asking up till what force blocks move together. So you assume they move together. Okay, get the friction in terms of applied force and apply the inequality that this friction, because it is static, because they are moving together, it lies between 0 and mu sn. From there you get the values of applied force. So we found friction in terms of applied force, and using this inequality we found the limits of applied force. Okay, so for these values of applied force, friction lies between 0 and mu n. It will be static, blocks move together. So up to 52 newtons, blocks move together. Beyond 52, they move separate. If you apply some 60 Newton or so, they'll move separate. Suppose if I apply 60, just for the sake of clarity, I'm doing this. Suppose if you apply 60 Newton, then you must draw separate free body diagrams. So on 5 kg, there will be a kinetic friction now, whose value we know, mu kn, 0.4 into 50, which is 20 newtons. So this acceleration will be 20 by 5, 4 meter per second square. What about lower block? Reaction of this friction will act here. Applied 60 is acting, is 8 kg. So its acceleration will be 60 minus 20 by 8, 40 by 8, or 5 meter per second square. That's how they move beyond 52 newtons. Are these values consistent? You see, you are getting for 8 kg a greater acceleration. So 8 kg is moving faster and it will rub 5 kg in the forward direction, which is correct. So it's consistent, the answers. So up to 52 they move together. Beyond 52 they will move separate. And we have done this problem assuming the case A, there is no friction between 8 kg and floor. But there is a case B also, where there is a friction between 8 kg and floor and it is 0.3. So how do we do that? So again, you assume they move together. So this is my 5 kg, this is my 8 kg. Okay. So let's draw combined free body diagram. There is F. Now there is a friction here. We gave the coefficient as 0.3. So if they are moving together, here friction has to be kinetic. Otherwise, how will they move? So the friction there is 0.3 into N. N is 130 newtons. So 0.3 into 130 is 39 newton. That is the kinetic friction. So combined acceleration will be net force F minus 39 by total mass, which is 13. Using this combined acceleration, we will get friction between the blocks here. So you can take either the upper block or lower block. Upper block will be easier to calculate. So there is friction. We already found the acceleration to be F minus 39 by 13. So I'll apply Newton's laws to find the static friction. So I assumed they move together and I got the acceleration. From there I am finding the static friction using Newton's second law. So force is mass into F minus 39 by 13. If it is really static, if they are really moving together, then this must lie between 0 and mu n. So 0 less than 5 into F minus 39 by 13 less than mu here is 0.4 and n is 50. So it is 20. So from here I get 0 less than F minus 39 by 13 less than or equal to 4. I divided with 5. From here I get 0 less than F minus 39 less than or equal to 52. From here I get 39 less than F less than 52. So from 39 to 52 they move together. What about F less than 39? They won't move because this friction will not allow them to, sorry, this friction will not allow them to move, this 39. So in the second case up to 91, we got 91, right? Sorry, 39 less than F less than 39 plus 52 is 91, my bad. So up to 91 they will move together. That is the second bit. So in these kind of questions, okay, in these kind of questions you should, no matter, even if you don't know the force, you should assume they move together, get acceleration, get friction in terms of applied force, then use the idea that this friction, if it is static, lies between 0 and mu n. This is the whole point. So let's go ahead. This we have done yesterday. Now let's look at this question. Again, this looks a bit more complex, so let's do that. I'll just erase the answer. We don't need answer right now. Okay, just keep it like that. Now let's read the question. In the system shown in the figure, so there is some figure given. There is 2 kg, 4 kg, some unknown force is applied, and there is friction between 2 kg and 4 kg also, and there is friction between 4 kg and ground also. So this is the figure. So in the system shown in the figure, part A, what minimum force will make any part or whole system move? So this is a very interesting question. I want the minimum force where at least something moves, either combined system or just the upper block. Something should move. That's my aim. It should not be stationary. So I want to find the minimum force where something should move. Either both may move together or upper may move separately, and so on. I want that to happen. That is one case. And second case is you have to find the acceleration and friction when applied force is 2 Newton. And similarly, acceleration and friction when applied force is 6 Newton. 2 Newton one case, 6 Newton other case. So this is what I have to find. Now, first let me do the A bit. So I have here the 2 kg. I have the 4 kg. There is coefficient of friction 0.2 here and there is coefficient 0.1 here, and you are applying F. First let us find what force is required to break the bonds here. The bond breaking force is the limiting friction there. If I calculate that, limiting friction, mu n, 0.2 into n there is 20. So 4 Newton is required to break bonds here. On the other hand, if you consider it as a single block, what force is required to break bond here? There is mu there, 0.1 into n, which is 60 or 6 Newton. So among these two forces, which will come first? 4 Newton comes first, because if you start increasing the force, first you apply 0.5 Newton, nothing moves because nowhere the bond has broken. Then you apply 1 Newton, again nothing moves. 2 Newton, 3 Newton, 4 Newton. When you reach this bond is ready to break at least. Okay, if you take combined system, this is not ready to break, it requires 6 Newton. But for 4 Newton, at least the the 2 kg is ready to move separately by breaking its bond with 4 kg. So the minimum force that will make the system move is 4 Newton. Okay, so slightly more than 4 Newton. At 4 Newton also it is ready to move slightly more than 4 Newton. What happens when it is slightly more than 4 Newton? Let's do an analysis. Suppose it is something like 4.01 Newton. Then 2 kg will move separately. There will be a kinetic friction here. That kinetic friction value will be 4. This reaction of this kinetic friction acts on 4 kg. Okay, but it is unable to break the bonds here because that requires 6 Newton. So this won't move. Only this will continue to move forever. This is exactly the case where I told you yesterday, right? There is a table and there is a book on it. You are applying force on the book. No matter how much force you apply, you cannot move the table. It's a heavy table. Okay, and on the table there is a book. Try moving the table by applying force on the book. You are free to apply any force on the book horizontally. You can't make the table move. That's exactly the case here. Up to 4 Newton, nothing moves. Slightly beyond 4, 2 kg moves separately. 4 will never move. 4 will never move. Because for 4 kg to move, you must break bond between 4 kg and floor. And that requires 6 Newton. So to break bond between 4 kg and the floor, you require 6 Newton to be applied on 4 kg. Now who can apply force on 4 kg? I cannot apply, F cannot apply. Only kinetic friction of 2 kg can apply force on 4 kg. That value is anyway 4. So on 4 kg, the maximum force upper block can apply is 4 Newton. But to break bonds here, it requires 6 Newton. So bonds can never break. That's the idea. So the first case is very clear now. 4 Newton will make the system move. Now, second case. What will be the friction and acceleration when you apply 2 Newton? So this is again very much doable. When you apply 2 Newton, you apply 2 Newton here. The friction here will adjust to 2 Newton. 2 kg cannot move because you need to apply more than 4 to make it move. So 2 kg cannot move. Reaction of this friction acts on 4 kg to the right, and ground will counter with another 2 Newton. 4 kg will also not move. So if you apply 2 Newton, then neither 2 kg moves nor 4 kg moves. Both acceleration will be 0. But friction on 2 kg and on 4 kg it will be 2 Newtons. On 2 kg friction is 2. On 4 kg there are two frictions. Friction due to 2 kg and friction due to ground. Both are equal and opposite. So that's the second bit. So it's relatively easier, the second bit, with 2 Newton. What about 6 Newton? When you apply 6 Newton, upper block moves separately, 2 kg. The kinetic friction is 4. So what is the acceleration? 6 minus 4 by 2, 1 meter per second square. What about lower block? It cannot move because to break the bonds you need 6 Newton, whereas you applied only 4. Okay, so this acceleration will be 0. So that is when you apply 6 Newton. So when you apply 2 Newton, nothing moves. When you apply 6 Newton, upper block moves, lower doesn't move. So this is the verdict. Now let's go down. More complex questions. So I have given the answers here. It is there. Now he has slightly changed the question. Instead of applying the force on the upper block in this example, he is applying the force on the lower block. And then let us solve all the bits. So now I have 2 kg, 4 kg, but I am applying the force here on the lower block. This coefficient is 0.2 and this coefficient is 0.1 as usual. Now the question is, I have multiple questions here. What force will make any part of the system move? I think that is one part of the question. Let's look at it. So A bit, where does sliding first begin? That means where does the bonds break first? He's asking us to find that. Then he's asking, what is the minimum force at which any part of the system will start sliding? Okay, these both bits are connected. Where will sliding first begin and how the system will move? Okay, at what force the system will start moving, either part of it or full system. Then C bit is, at what value of F will sliding start at other rough surface? So if sliding first starts between the blocks, then he's asking when will sliding start between the lower block and ground? Or if sliding first starts between lower block and ground, he's asking when will sliding start between upper and lower block. So these are the things. And then for the following value of F, find friction and accelerations, and he has given really lot of bits here. So I'll do the analysis. This is a bit complex analysis, so let me just go step by step. So here first, the bonds have to break here only first. Without bonds breaking here, how can bonds break here? Not possible now. See, I kept a book on the table and I am pushing the table. Without the table moving, can the book move? No way. Suppose this is the table and this is the book and I am pushing the table. Table itself is not moving. Can book move? There is no other force on the book. I am pushing the table. So book cannot move. So first bonds have to break here. And what is the bond breaking force here? Mu is 0.1 into N is 60. So 6 Newton. So you need 6 Newton or slightly more than 6 Newton for the system to move. So for F slightly greater than 6, system means both the blocks starts moving. So I am sure of one thing, 0 less than or equal to F less than or equal to 6, nothing moves. F greater than 6, movement starts. This much I know. Movement starts. Now once motion starts, initially both 4 and 2 kg might move together. Okay, 4 kg is taking 2 kg along with it. Why it is taking along with it? Because its acceleration is less, applied force is less. But if you start increasing the force F, if you make it very huge, then there comes a point where the table just starts moving much faster and the book relatively moves much slower. See, it is possible sometimes you are moving the table very fast, some utensil on the table might fall down. It's unable to keep up with the table, right? Suppose there is a table in the kitchen and you have kept some utensil on the table and then you start moving the table very fast. This utensil will slip on the table. They don't move together and eventually the utensil may fall down. So for lower forces, these two might move together. But as you keep increasing the force somewhere, the 2 kg also will start slipping on 4 kg. That's what we are looking at. So first is up to 6 Newton, nothing moves. F greater than 6, okay, the table, the lower block starts moving. Then as you continue to increase the force, somewhere the upper block also starts slipping with respect to lower. So I want to find where is that force? What is the value of that force? So I am doing now F greater than 6 Newton analysis I am doing. I want to find out at what force both move separately, both the table and the, not the table, I'm sorry, both the lower and upper block They start moving separately. I want to find out. Okay. So let's assume they move together. I draw a combined free body diagram. So I am applying a force greater than 6. I'll call it F only. And kinetic friction here is 6. Okay. And total mass is 6 kg. So the combined acceleration is F minus 6 by 6 net force by mass. Using the combined acceleration, let's get the friction between the blocks. I'll take the upper block. So I'll take the 2 kg block, upper block. There is a static friction on it. I am assuming they are moving together. Okay. Assume they move together. So acceleration, we have found the combined acceleration. Let's apply Newton's laws. Net force is mass into acceleration. That is F minus 6 by 3. But if it is really static, if they are moving together, they should lie between 0 and mu n. What is mu between the blocks? 0.2 into 20. N is 20. 4 Newton. So from here 0 less than F minus 6 less than or equal to 12 and 6 less than F less than or equal to 18. So up to 18 Newton, these blocks move together. Okay. So anything less than 6, they won't move. The moment you apply force greater than 6 and up to 18, they move together. Beyond 18, what will happen? The lower block will move separate, upper will move separate. It's like if you apply a huge force, the table moves faster, it moves separate. The utensil on the table moves separate. It's like that. So my analysis is now complete. So let me write the analysis. 0 less than F less than 6 Newton, nothing moves. First, you should get this kind of analysis in these problems. Then 6 less than F less than or equal to 18, both move together. Then F greater than 18 Newton, both move separate. I got this complete analysis. So that is the first part of the question. Okay. Where does sliding first begin? Sliding will first begin between lower block and ground. What is the minimum force at which any part of the system starts sliding? Slightly more than 6 Newton. Where will sliding begin at other surface? 18 Newton. Then next bit, find the acceleration and friction when F is 3 Newton, 12 Newton, 24 Newton. Now it's easy. Suppose I take 3 Newton. At 3 Newton, nothing moves. So acceleration of both blocks is 0. There is a friction here, static, which is not allowing the lower block to move. So friction on lower block is static and 3 Newton. And for the upper block, there is no friction, right? Friction on upper block is 0. When will there be friction on upper block? When there is slipping between upper block and lower block, there can be friction. Or if you apply a force directly on the upper block, static friction may counter it. Right now nothing is there, so no friction on upper block. So this is first case. Then what about when F is 12 Newton? Okay, when F is 12 Newton. So when F is 12 Newton, both move together. Okay, both the blocks move together. 2 and 4 kg. So there is a kinetic friction of 6 Newton here. So acceleration is 12 minus 6 by 6 or 1 meter per second square. This is the combined acceleration. Up to 18 they move together. Just excuse me. చెప్పమ్మా. తెలీదమ్మా. వచ్చి చూస్తాను, నేను క్లాస్లో ఉన్న తర్వాత చూస్తాను. So we got the combined acceleration. Now with this acceleration we'll find the friction. You can take the upper block, 2 kg friction. We got the combined acceleration as 1. So they are moving together now. So this friction is static. And what is the formula for static? No formula. You have to use Newton's second law to calculate it. So F is mass into acceleration, that is 2 Newton. So there is 2 Newton friction on the 2 kg. On 4 kg, there is reaction of this friction, which is 2 Newton. And there is bottom 6 Newton kinetic friction. Applied force is 12. Okay, and its acceleration is also 12 minus 6 is 6 plus 2 8. 8 wait a minute. I Something is wrong. This 2 Newton I wrote it wrong, right? This should be in the reverse direction. Sorry, my bad. So what is the acceleration of 4 kg? 12 minus 2 minus 6. 12 minus 8 by 4. That is 1 meter per second square. Perfect. So when you apply 12 Newton, combined acceleration is 1 meter per second square. Friction on upper block will be 2 Newton. Friction on lower block will be 2 due to upper block and 6 due to ground. This is the verdict. Now third case, he is applying 24 Newton. In this case, upper block will move separately, lower block will move separately. He is applying 24 here. So here there will be a kinetic friction because lower is pulling the upper. There is slipping. So there will be kinetic friction. What will be the value? Mu n. Mu is 0.2, n is 20. 0.2 into 20, 4 Newton. So upper is 2 kg. So its acceleration will be 2 meter per second square. Reaction of this acts on lower block. There is a 6 Newton force here. This is 4 kg. So acceleration of 4 kg is net force 24 minus 10 by mass, which is 4. 14 by 4. It is 3.5 meter per second square. This is for the third case. So we have all the three cases now I have done. If you go and check the answers, uh, all the cases answers are here. Now, two block systems have not ended. Let's try one more question in two block system. Uh, One very interesting, tricky question. Then we'll go to three block. It's a very complex assignment. Let's try to do this question. I want you to give a try to this question. What you have to find? You have to find the acceleration of both the blocks and the friction acting on them. Okay, 2 kg, 3 kg blocks are there, coefficients are given. So find acceleration of blocks and friction on them. Can you give a try to this? చెప్తాను. ఓకే, ఓకే. చెప్పు. వినపడుతుంది. వినపడుతుందమ్మా. వినపడుతుంది, చెప్పు. ఓకే. సరే. ఆ, సరే, సరే. నేను క్లాస్లో ఉన్నా కదా, వాళ్ళు ఏదో ఇలా అడుగు ఇప్పుడే లాస్ట్ వచ్చింది. ఆ జయరాం మా ఇంటికి వెళ్ళినట్టు. ఉమ్, ఇంకో హాఫ్ అన్ అవర్. So are they moving together or no? We first start with that assumption. No? So let's draw combined free body diagram. Here there is a kinetic friction of 5. So combined acceleration is 15 by 5, which is 3 meter per second square. Using this combined acceleration, let's calculate the friction between 2 and 3 kg. So if I take 2 kg free body diagram, there is 5 Newton. Because we assumed they move together, we are assuming friction is static. No formula, we have to calculate it using acceleration. So A is 3. So 5 minus F is mass into acceleration. So F, oh my god, this is a big problem. F is coming out to be -1. Okay. So I don't think that is possible. So immediately what we should do, we can't take force like this and get it negative. So immediately what is your thought process? Maybe the friction on 2 kg is to the right. That's possible, na? Why you are taking it to left? Friction on 2 kg may be to the right, because 3 kg may be moving faster, was trying to move faster, and it is carrying 2 kg along with it. So let's try that. That means, so combined acceleration is fine, no problem. Combined acceleration is fine. But when I am drawing the free body diagram of 2 kg, how should I draw? 5 Newton and friction in this direction, and acceleration is 3. Can that be possible? Yes. How can friction on 2 kg be to the right? Because 3 kg is trying to take it along with it, right? 3 kg might have greater acceleration, and uh, I mean, both have common acceleration, but 3 kg might be trying to take 2 kg along with it. So if I apply Newton's laws now, what do I get? 5 plus F is 6. So F is 1 Newton. Is it less than mu n? Is this friction less than mu n? Mu is 0.3 and n here is 20. Okay, I'm talking about here. So mu is 0.3 and n is 20. 0.3 into 20 is 6 Newton, which is fine. So our friction is less than the limiting friction, so they move together. So combined acceleration is 3. So combined acceleration is 3 meter per second square. They are moving together. Friction on 2 kg is to the right, 1 Newton. Friction on 3 kg due to 2 kg is to the left, 1 Newton. Friction on 3 kg due to ground is 5 Newton kinetic. Okay, so a bit tricky, because the moment you took friction on 2 kg to left and tried to solve it, you got it negative. That's not possible physically. So we reversed the direction and recalculated it. So that's regarding, you know, so sometimes there can be these kind of tricky questions. Suppose I asked you find friction and acceleration for this case. So I am focusing extensively on two block systems because first you should be thorough with them before we go to three block systems. So try this. Again, best assumption is assume they move together and do it first. If it fails, then go to other assumption. So are they moving together? Just want to check.
No, sir.
No. Okay, let me check. 30. The kinetic friction is 5. This is 5 kg. So combined acceleration is 25 by 5, 5 meter per second square. So I'll take upper block, 5 Newton, friction 2 kg, acceleration is 5, 5 minus F is 10. Again the same problem. F can act the other way. Okay. Oops. 5 plus F is 10. F is 5. Is it less than mu n? 0.1 into 22. Wrong. They don't move together. So now is the tricky part. They should move separate. So try to find that. When you're drawing separate free body diagram, again, the problem is, what is the friction direction between 2 and 3 kg? Now it is kinetic friction, but still, uh, is it acting on 2 kg to the left or to the right? We don't know. So we have to again take something and verify it. Now, this is a bit tricky. These kind of questions are a bit tricky.
Sir, is friction 2?
Okay, let me calculate. I am not sure actually. Let me calculate. So one thing is clear, they move separately as you said. They won't move together. So upper free body diagram I am drawing now, 2 kg. There is 5 Newton. I'll assume friction to the right. I don't know. Kinetic friction now. So mu n. So zero point 0.1 into 20, that is 2 Newton. So acceleration is 3.5 meter per second square. Then the lower block, I am applying 25, and the reaction of this friction is 2. Here kinetic friction is 5, 3 kg. So its acceleration is 25 minus 7, 18 by 3, 6 meter per second square, right? Now let's check, is it consistent? Are our accelerations and friction directions, are they consistent or not? We will check. Now the lower block has got a greater acceleration, so it's moving technically faster in a given time than upper block, so it's going to rub the upper block to the right, and hence this friction is correct. So 2 Newton, and I got the accelerations. This is the correct result. Now sometimes people take, because this also you have to verify again, even after they are moving separate, friction directions and accelerations, are they consistent or not? Sometimes by mistake, suppose not by mistake, suppose you try to take friction on 2 kg to the left, for example. Let's say they are moving separate, so it's a kinetic friction of 2 Newton. Then acceleration will be 5 minus 2, that is 3 by 2, 1.5. And for the lower block, you got 25, and the reaction of this is 2, and here you got 5, and you get its acceleration to be 22 by 3. 25 minus 5 is 20 plus 2, 22 by 3. Now this has a greater acceleration than that, so this is moving faster than that. Then how can the friction on this be to the left? It has to be to the right, because the lower block is kind of moving. If I keep two palms like this, if lower is moving faster, it will push the upper palm to the right, right? So this cannot be wrong. So this cannot be right. This is wrong. So only this is correct. So that is the uh, fine point here, the technicality. That is the technicality here. Okay. One last question on two block systems. We'll take up three block tomorrow, because these are really important. Two block. We should first master two block before we go to three block. And I feel in your exam, if at all they give, because it's a time constraint, they might give two block only, not three block. So you try this. I feel they will move together, is it not? Suppose I take combined free body diagram, 10 Newton. Here there is a kinetic friction of 5 Newton.
Yes, sir. They move together.
They move together, correct. So acceleration is 1 meter per second square. Now you take the upper block. Let's take friction static to the left. Acceleration is 1, 2 kg. So 5 minus F is 2, F is 3. Is it less than mu n? 0.3 into 26. 3 less than 6. Perfect. So they move together and combined acceleration is 1 meter per second square. So two block systems you have mastered. We'll take up three block systems in next class. I'll confirm whether it is tomorrow or otherwise. Uh, but we have now only three block systems left and a couple of other small things before we wrap off this. So one class more. I'll not do too many three block systems. I'll do two good quality problems actually, and we'll conclude with that. And some little tidbits we will do and conclude. So friction will be done with that. Then we can go to work energy. Okay, let me just PDF this and give it to you.